Hello, students. We're going to be talking about section 12.5, which are reaction mechanisms. This is a really interesting part of the chapter because now we finally get to ask the question, why? Why do reactions have a certain order? Why is one second order and another one's first order? So that's what this section explains. It does require us, though, to adjust some thinking that we might have been doing without even realizing it. And that is that a balanced equation does not really tell us which molecules might be colliding with which molecules to make product. In other words, a balanced equation is very useful, gives us mole ratios, tells us how much product we make, but it may not give us the nitty gritty of how products are being made, like what are the individual steps that it goes through to make those products, who's colliding with who. So even that might sound a little funny. So I think what I'd like to do is to go with a problem that we've already done. This question here is from your in-class questions, Zoom questions, I call them. Now, this was number 2. The numbering here is a little bit funny, but this was actually number 2 from the Zoom questions. And it was one that I addressed in a previous PowerPoint. And we did this one in our discussion section, essentially. Okay, so let's take a look. Let's just review it real quick. No harm in that. Between experiment 1 and 2, these guys are the same. This one doubles. This one goes up 4 times. So with respect to NO2 up here, the rate equals K NO2 to second order. Okay, now let's take a look at the other ones. We have to find where NO2 is the same, so that's these two, that's the same. This CO doubled, and then the rate stayed the same. So then we concluded that it's 0 order for CO. So maybe this is ringing some bells now. We did do this one. Any concentration to 0 exponent is 1. So I don't even need to write that one in. So our experimental rate law is that it was second order with respect to NO2. Okay, so that's where we left off. Today's question is why? Why is it? That's our big question. And I think a good way of looking at it is, let's look at the balanced equation. Doesn't it seem odd that CO does not play a role in the rate? Right? Why is it 0 order? So why does CO2 not play a role in the rate law? Okay, so that is a really good question. And what I'd like now for us to do is to think about a very interesting point. And I know it's a little overwhelming to learn how to do methods of initial rate and graphing. It's very highly mathematical, but now we're going to stop and kind of think of what's going on on a molecular level. Okay, if I look at the balanced equation, if I'm looking at it, I might assume right, that NO2 collides with CO to make product. Okay. And I think that that's a good thing to start from because that's probably what we and all of you think and what it makes kind of sense, right? We're looking at the balanced equation. But let's take a moment and think about one thing, and that is that if NO2 collides with CO to make product, and that's your one reaction, one step process. So if it's a one step process, wouldn't the rate depend on both? Right? Wouldn't it depend both on NO2 and CO? So, in other words, we would probably think the rate law would include that CO in some form. So, that should be wouldn't the rate law depend on? So, it's more of a question format. So, let me erase that. Whoops. So, if NO2 collides with CO to make product in a one-step process, we would expect that the speed of reaction would depend both on NO2 and CO. But let's take a look. Our experimental rate law, our experimental one. Not only does it not depend on CO, right? CO was out. It's NO2 to the second order, not first order. And so what we're seeing here is that the rate law suggests that something else is going on. So the rate law suggests a different pathway. And the word I'm going to switch it to is mechanism for making product. So the mechanism is going to be a play-by-play, nitty-gritty, down to the details of really what's going on behind the scenes to make those products. But the number one thing is that the kinetics data reflects that. So in other words, the rate law suggests what's going on in the mechanism. Okay, this is a really difficult thing at first for students. I think for a number of things, we get very attached to these balanced equations. So you look at NO2 and CO, you'd never think that there's probably something else going on there. So what I'd just like you to think about is we're adding on a new thing. So this is very new. The way I kind of see it is that, let's say you're watching a movie. A movie looks very seamless and it goes through the story and all the action, etc. But the way they made that movie was very different than what we see, right? It has all sorts of stuff and they take it in scenes and they have to redo it. It's very different. So looking at this balanced equation, the balanced equation tells us a lot of really important chemistry, but there's a behind the scenes that's not showing up here on how these guys are really reacting. Now, that's number one. Number two, the kinetics, the rate law has to match what we think's going on a molecular level. So the good news is no one's going to ask you, hey, what do you think? What do you think the mechanism is? What steps are involved in making product? No one's going to ask you that. Instead, what we're going to do, and I'm going to switch to the next slide, is you're going to be given this mechanism. And I'm going to write up here in the corner, experimental rate law. That was based on data. So this mechanism is given. Most likely this was somebody's PhD, their life for like 6 years, trying to come up with this mechanism and prove it. And so no one's going to ask you to come up with the mechanism. But when we look at this, what we're seeing is a couple things. This proposed mechanism has the reaction occurring not in one step, but in two. So let's kind of go through what they outlined. Step one is NO2 collides with NO2. And it makes NO3 and NO. Now, if you're noticing, NO3, that's not nitrate. NO3 is a strange oxide of nitrogen. You probably, if it looks kind of misspelled to you and funny, it's because it's not super stable. So what happens in step two, do you notice the NO3 collides with CO to now make NO2 and CO2. So first of all, what we're seeing here is that step one makes what's called an intermediate. It's formed, but then immediately consumed. Okay, now if I think of it like this, where NO3 is formed and NO3 then is consumed, I can cross it out. And then I can write the overall equation. So if I notice step one has two NO2s, but do you see how one's a product on this side? So I actually could cancel out the NO2. So my ultimate equation overall is NO2 plus CO to make NO and CO2. So this is the balanced equation. The other thing that we're seeing is that it is very common to have what's called an intermediate. It's formed and then consumed. Intermediates do not appear in the balanced equation. Okay, now the business with the NO2 canceling, you could also look at it like this, that you have two NO2s here and that you formed another one on this side, but then one of them cancels. So if you like that better, that's fine. Either way that you want to think of it, I'm going to erase it, but because I think it's just easier to look at it from the original two steps. Okay, so each of these steps is what's called an elementary step. Elementary steps are the play-by-play of who's colliding with who. And in this mechanism that's proposed, the NO2 does not collide with CO at first. It collides with another NO2. Then it makes one of our products and this intermediate. The intermediate then collides with CO to make CO2, the other product. Okay, so with this in mind, how does this explain and how will this align to our experimental rate law? Because that's what proves that this is true. So the experimental rate law has to match what's going on in this mechanism. And for this, we will need to think of one thing, and that is that the rate law for the elementary steps we can get from the mechanism. So our elementary steps we can write a rate law for. We can't do this for the balanced equation overall. That's a no-no. That's from data. So the rate law for the overall equation we get from data. But the elementary steps, we can write a rate for them, and we pull it from what's going on, who's colliding with who. So NO2 is colliding with NO2, and because that is on a molecular level, if I double NO2 and I double the concentration of NO2, well, I would double this and I double that, and the rate would go up 4 times. So I could just write that one as NO2 squared. So the rate law for elementary steps, we pull from the actual equation. And I know that's a little confusing because we can't do that with the real equation or overall. But elementary steps, since they're telling us on a molecular level who's colliding with who, then we can determine the rate law from looking at it. Now, a couple of comments on this. There's some other terms. This elementary step is said to be bimolecular. We'll come back to those terms in a second. There's a chart that highlights it, but I'll just write it here. This just means 2 molecules are colliding. Bimolecular is always second order overall. Okay, let's look at the second one. Rate would equal K NO3 to C times CO. Okay, just pulling it from the elementary step equation. If we double NO3, the rate would go up twice. If we doubled CO, the rate would go up twice. In other words, first order for each as written. That one's also bimolecular. And overall, second order. Overall, because that's 1 and 1. Okay, so here's our important part. Step 1, if you look at it, do you see how the rate law matches the experimental rate law? And why is this the case? Well, there's one thing that I'm going to add in here. The reason why that's true is because step 1 is the slow step of the reaction. Oops, I spelled mechanism wrong. Okay, so step 1 is the slow step in this reaction mechanism. Okay, now how will I know that? Hold up. Okay, so let's stop here for a second. Every reaction usually has more than one step in the mechanism, but they're not all equally efficient. Each of them has its own activation energy. So in this case, step 1 is slower than step 2. And the way that I know that is because step 1 matches the experimental rate law. So here's our key concept. The slow step is the rate limiting step. The rate law of the slow step will equal the rate law experimental. Okay, now at this point, usually students are a little bit, I don't want to say panicked, but they're like, oh my goodness, what is this? What's going on here? Okay, so there is some good news here, is that once you get this, these are actually way easier than what we've been doing the whole chapter, because you either figure out which one's slow because you write out the rates for each step and see which one matches experimental. So you see how these are the same? And since they're the same, we conclude that step 1 is slow because that's going to limit our rate. The other way around, we're going to see in the next one that we're going to do, is you could be given which one's slow and then figure out what the experimental rate lies. Now, why does the slow step limit us? Because if it's